This video will illustrate how Origin's CheckMate software encompasses the concept of the digital thread, consuming the part manufacturing information created in SOLIDWORKS and driving it through the quality process using CMMs and/or laser scanning technology, delivering better parts faster and more efficiently. Noticing at the top the toolbars and ribbon tabs, you can see that CheckMate is directly integrated into the SOLIDWORKS environment. Now over on the left side, you can see SOLIDWORKS DIM Expert Tree containing the PMI. In the center of the screen is the CAD geometry with the PMI shown graphically as the annotations. On the right-hand side is CheckMate's programming browser. Now the first step is to create a CheckMate program by populating the programming browser from the PMI automatically with the press of a single button. CheckMate consumes the name, tolerance, and reference information as it reads down the DIM Expert feature tree, extracting the nominals from the CAD model, and then adding CMM sensor information such as approach, retract, number of hits, depth, clearance heights, and more from the CheckMate defaults, and creates the resulting feature measurements in the programming browser. Now the contents of the programming browser can be seen graphically over here on the CAD part. These gold items are the feature measurements, and the blue lines connect them, allowing you to graphically see the sequence or order of the program. The programming browser is Windows-like with folders and fully editable measurement features, and is used as an interface to enhance programming functionality. The order of the program can be edited simply by taking a feature and dragging it up anywhere within the browser. Measurement features also can be moved around on the CAD simply by clicking on them, moving them over a little bit just to fine-tune the program. Switching to another part. To complete this program, all I had to do was define some CMM-dependent variables, like how the part sits on the table and what measuring probe I'm going to be using. At any time, we can simulate the program in part or in whole via the programming browser, including collision detection and avoidance options. Then, when we're happy with the program, it is posted out to any modern DCC CMM machine to be executed. No code to sort through, and no DMIS expertise is required. Now this same program can be used as a soft gauge for laser scanning technologies and other forms of dimensional measurement equipment. What you're seeing now is a point cloud mapped onto the solid model showing deviations of the scanned part to the nominal CAD. This pretty picture provides a quick visual indication of what's going on with the part. Green is in tolerance, red and blue is out of tolerance. But generally in manufacturing, part approval or design corrective actions, more detailed information is required. So CheckMate can use our program as a soft gauge, and results data or substitute features are automatically extracted from this point cloud. The end result is that you get a detailed inspection report right here in CheckMate's reporting browser, whether you collected the measurement results using the laser scanner or the CMM. I'm just going to open this up a little bit, and you can see the PMI feature names and tolerances are carried through the entire process. Now, this reporting browser is fully customizable. We can add more columns, and have this report looking exactly the way you'd like. Now CheckMate can create other types of reports also. Now I'm just going to turn on a Whisker Report. So what you're seeing here is a whisker report where the lengths of the whiskers are scaled but indicate direction and magnitude of the deviations. The colors green, red, and blue indicate intolerance and out, high or low respectively. Another report that we can do is an Excel report. And in this particular template, which is a 9102, is just one of the many reports that we have to offer. Switching to a final part, when determining corrective action for design or manufacturing, it's critical that all decisions be based on an average of a sample and not on a single and possibly out-of-spec part. This color map is showing the average of deviation of 5 scanned parts. Now let's look at the reporting browser one more time. Now we're going to look at some SPC data. You can see in the samples column we have 5 individual parts. I'm just going to turn those off. So now what we see is the averages. And now we're seeing statistical information. You can see this X-bar column, which is like a histogram looking straight down. The red and blue are control limits. The magenta color is the mean. We can turn on statistical things now to look at, such as CPK, PPK, standard deviations, and we can even select process tolerance, which is suggesting a possible best tolerance that should be used based on the sample. Now, using a tool like this is critical because we don't ever want to make any changes to the design if we haven't made the manufacturing process itself stable first. So in summary, we've shown how the digital thread originating with the model-based definition PMI can be driven down through the quality process, and how the measurement results can be brought back upstream and used to form the basis for better decisions involving part and process improvement, all within SOLIDWORKS. Thank you for your time.